in about, I'd say, okay, Mark, everything we're going to say from here on in is broadcast. You ready?
Ready.
Okay.
Too much fun. Set that slow so that we can do that. I thought that stuck. I thought, don't you stick now. Okay.
Looks good.
Put it in the over 70 mode. Nice and slow.
Well, that works good in the 50s too. Seems to be working. Everything behaving normally.
Pretty low flow rate. 2 and 5. Nice differential.
Can I borrow the mouse?
Yep.
Back to you.
Like my new arrows?
Very good.
Took me a while to figure that out on the machine, how to make an arrow. But
Arrows help.
well, it just kind of helps everybody understand where it's going.
Direction of flow.
I didn't realize that this stroke indicator is magnetic. Makes it nice and easy to play around with.
Yep. Okay, here we go. Hello, this is Carl from lunchboxsessionscom.
Oh, and this is Mark Many Letters. I'm here having fun with Carl today for all of you who've joined us, and we're really happy to see you.
We had Mark with us last time around, as you'll probably recall, and this time we got him a headset microphone, so we're all set to work together.
Turn this down.
And we're sure glad you were able to join us again this year. Thanks for being with us. If you followed us through the entire series since the beginning back in early April, and also welcome if you're new. This is our 8th video episode, our 8th live broadcast, and it's been an exciting time to put these together for you during a difficult time for so many of us with the pandemic happening on a global scale. So great if these sessions help you with some of your learning needs, and we'll continue into the fall season. We haven't quite got our dates and topics all sorted out, but keep track at lunchboxsessions.com/live, and our list of topics will show up there. And we'll have something happening again near the end of September and on through the fall, at least one per month. So far, thank you for joining us, viewers from Oman, from the Philippines, from Tunisia. That's fantastic. From Congo, in Africa, terrific. Russia, Poland, Jordan. Viewers from the United States and India, and what do you know, from Red Deer. Hey, those might be folks from our own team up in the front office.
I see them over there.
Thank you for joining us on today's broadcast. Today's topic is an interesting one. It comes up in so many conversations that we have with you as you converse with us, as you send us emails or inquiries. And today's topic is load sense hydraulics. Very popular way of putting a hydraulic system together for agricultural machines, mining machines, construction machines, And we even see it showing up from time to time as well in the stationary or the factory environment. And it's a dynamic area to work in. Lots to cover. Mark and I are going to try to keep the topic simple. That in itself is going to be a hard thing to do. It's going to be hard to keep it simple. And we'll probably end up, as we usually do, covering too many things in the course of our short hour and a quarter or so together. But remember to fire your questions to us on the chat, and that will help too. We'll try to address as many of those questions in the chat as we can, especially if they're on the load sense hydraulic topic. If you've got other questions for us about our equipment or other things that we do, or the Lunchbox Sessions software or our company, be great if you'd fire those to us in an email. info@lunchboxsessionscom is a great email for that. Or look for Mark Manny Letters or myself, Carl, on LinkedIn and send us an invitation to link, and we can also continue our chat that way as well. Yeah, load sensing systems. Here we've got a couple of just major components from a load sense system. Here's a load sense capable pump, and this is where the load sense signal line would be connected, coming from some type of proportioning valve. Could be something as simple as a needle valve, but in most cases it'll be a multi-section valve bank, and that load sense signal line will enter here and work with the pump's controller to make very small, in some cases very small, subtle changes to the pump's control and the swash plate. And you're going to see Mark adjusting the standby or the margin pressure. Oh yeah, lots of terminology for us to straighten out in this one. You're going to see him put a very small wrench on there on our power unit shortly, making adjustments to the load sense controller. Here's another common load sense capable pump you might recognize, and the load sense signal hose would enter in there on the pump's controller. Over here we've got a multi-section valve bank where there might be several different levers, only a couple of sections, 2 sections on this one. Maybe on a grader it could be 6 or 8 sections wide, lots of functions. And if there's the load sense port where that signal line would leave and travel back to the controller on a pump to make up a complete load sense system. Makes it seem so simple. If it's just a hose that goes from the valve bank to the controller on the pump, you'd think there's nothing to it, right? And yet sometimes it gets pretty tricky, as you and I know. Hey, let's have a look here. We've had others join us from Bahrain, fantastic, from Colombia in South America, from Sweden, from the UK, from Brazil, fantastic. And Michael Ferentz has joined us this morning from Fluid Power World magazine. More about them in a moment. Good morning, Mike. Great for you to be able to join us. Indonesia, participants from the Netherlands, from Algeria, from India. Fantastic. All right, let me check my notes and remind myself of where I was headed here this morning. So load sense systems will save you some fuel, will save you some electricity if they're powered by an electric prime mover, and hopefully also save you some heat, some inefficiency. But things can get a little bit confusing at times when you're troubleshooting. So Mark and I are going to try to give you a few basic pointers to help clear up some of the adjustments and issues that you face along the way. We're just going to focus primarily on how load sense systems work. Because as Mark and I often say, half the battle in troubleshooting is
knowing what normal is.
Knowing what normal is. Yeah, if you know your normals, how the system is meant to be set up, what to observe for a normal functioning system, how it works, that's a lot of the battle in the world of troubleshooting. On YouTube, you may need to log in to your account or to your other Google services in order to be able to use the live chat and send us your questions. So feel free to do that, and thanks for telling us where you're from. Welcome participants from Germany, from Venezuela, from Namibia. Fantastic.
Always have to go home and do a geography lesson sometimes.
There you go. Lots of geography, you bet. Our sponsor today is Oil Gear. For over 100 years, Oil Gear has been engineering industrial products for extremely challenging environments, from the depths of subsea work to moon exploration. Pulp mill bale presses, steering pumps on mining haul trucks, and many other heavy-duty, continuous run applications feature the reliability of oil gear engineering. The world demands oil gear. Also, I'd like to give a shout out to my friends at Fluid Power World. FluidPowerWorld.com is a great website to have a look at. Fluid Power World is your resource for fluid power components and for expertise on system design and engineering. If you have a look at the events tab on the FluidPowerWorld.com website, you will see that the Fluid Power Technology Conference is virtual, is online this year, as so many conferences are. It's been going on now for a while this summer. There's been a number of great presentations. You'll want to join in on those. The next one is Tuesday, September 1. Brandon Richards, the CEO from Panelin America, will be presenting. You won't want to miss that one. FluidPowerWorld.com. Check the events tab and the events link and join up for the Fluid Power Technology Conference. As we usually do, as we're getting underway, we have a look at some photographs of common load sense machines, just so we can remind ourselves of what it looks like out there in the real world. So I'm just going to switch over to my photos here. And these are photos that Mark and I have collected over the years in our travels, just to sort of remind you a little bit of what load sense machinery might look like in a typical final build or installation. And what you see there in the middle of the screen, if my cursor allows me to sort of follow along on a hose, hopefully you see that. You'll see that LS signal line coming back from some kind of flow proportioning valve, entering back in and connecting up with the pump controller on one of two pumps. The more outboard pump of two through-mounted pumps only has pressure compensated feature. But the one that's more closely coupled to the prime mover, that one has the load sense line coming in. Let's switch over to our next one. Here's from a Caterpillar grader. You might recognize this one. One of two main piston pumps on this particular machine. And there it is again, that load sense line. You can see it here just above the yellow controller on the pump. That load sense line is coming back from the main valve bank, taking information from the most heavily loaded cylinder or hydraulic motor on the machine and using that signal pressure to basically adjust the pump on the fly. It's really not too much more complicated than that. A load sense system, by some description, is still a pressure compensated pump, but it's constantly being readjusted based on how hard the work is at the hydraulic cylinder or the motor. We'll try to keep it simple when we can. In fact, in terms of keeping it simple, let's have a look at a super simple hydraulic system. This is the load sense hydraulic system for a generator set. Can you believe it? This particular pump that you see there just below the pressure gauge is a variable displacement pump, and it is sending flow through a 4-port 2-position hydraulic valve and off to a hydraulic motor that you see there just below the letter G. What's happening? Well, this hydraulic motor is powering a generator set. And so one of the big advantages for working with a load sense system is not just about the energy savings. That's a big one. But another thing that a load sense system can do is very carefully regulate flow in the face of changing load pressures on that actuator. And so as that hydraulic motor is turning an electrical generator, it's coming under different amounts of load depending on what's been plugged into that generator. And so here's a simple load sense system. And if you're looking at this schematic and wondering where's the load sense technology, well, it's all clustered near that pressure gauge. So as much as many load sense systems that you might be familiar with have a multi-section valve bank, like on a grader or an excavator, let's say, in this case, look just above the 12 o'clock outlet port position on that pump and notice that there's an orifice there. You might say, is that a needle valve? No, not in this case. It's not even adjustable. It's a fixed orifice that's creating the pressure drop necessary for us to create a load sense system. And then you see that red line moving off to the right and wrapping around that dashed red line, moving around and back into the pump's controller. That's the load sense part of this circuit. It's all fairly compact. So let's see it on the actual machine. There we go. That's the generator, that aluminum disc, and the black structure that moves off into the upper right-hand corner of the screen. And then, for those of you who know your bent axis piston motors, there it is. It's turning that particular generator. There's a bypass pressure relief valve there. There's an anti-cavitation check valve built into that beige colored valve block that's on the inlet of that motor. But as we move back towards the pump for this system, the load sense capable piston pump, what you are seeing there, it's all kind of painted black, so it might be a little difficult to see some aspects of it, but flow is moving from the pump on the right out through that fixed orifice, not even a variable needle valve, just through a fixed orifice to set the flow rate and create that necessary pressure drop. Mark's going to have more to say about that. And after passing through that fixed orifice, there's our load sense line. It's not even a foot long. It's not even 30 centimeters long. And back to the controller on the pump. I think in our travels, Mark, this is probably the simplest plumbing we've seen.
I haven't seen one simpler than that.
For a load sense system, yeah. And if you're wondering what that T-fitting is, where's that going? That's just going to that gauge that you saw on the schematic a moment ago. That's going up to a gauge on the operator's console. Here, I'll back up. So that gauge that you see the 800 pressure value for, it looks like it's just connected directly to that T-fitting, but it's actually on a hose that goes up to the operator's console. So that is our brief look at load sense systems out there in the real world, just to remind us a little bit of what the applications actually look like.
Carl, also go back to the schematic for a second.
Okay, let's do
just to show a good example of the simplicity of this particular symbol. Now, this pump is much more complex than that symbol represents, but often you will just see what looks to be a pressure compensated pump symbol and just have the additional pilot line coming off it. You need to do your homework on your systems to determine what kind of pump you actually have. But this would tell anybody who's familiar with load sense systems, that's what we have, a load sense system. But it's not going to be that simple.
Yeah, that is a good that's a good point to make, Mark, that pump symbol is overly simplified.
Well, I know we're going to get into
a
little more complex ones.
The pump symbols are going to show up here in a moment as we get into our material, and we'll see that there's generally a few more elements that are involved with the drafting of that symbol if it's complete, as Mark has pointed out. All right, let's switch over to lunchbox sessions, and let's dive into a simulation that will help us understand a bit more of the realities of how a load sense system is working. I hope that's showing up correctly for everybody's screen there. And this is one of our simulations where we've got a piston pump being featured in the middle. Maybe we'll zoom in as we move along here a little bit. And then flow passes over to the right through a proportional valve spool. The assumption with the vast majority of load sense operated or load sense controlled hydraulic systems is that you're likely to change the speeds as you desire to hydraulic cylinders or motors. And in this case, instead of that fixed orifice, because the genset motor only needed to turn at one speed, in this case that's been replaced with a fairly complex looking proportional valve spool. And what you'll notice is that we don't yet have a load sense system. There is no feedback line present yet. We're basically working with just a pressure compensated pump at this moment. Now on the graph over on the left, you'll see a couple of colors there. That yellow color area represents the pressure that's happening on the business end of this hydraulic system right now. And that's out at the cylinder. So our cylinder only needs a minimal amount of pressure right now to move. The cylinder is lightly loaded. That pressure value you'll see along the horizontal axis on the bottom where it says pressure at cylinder. And the flow rate is also well below the maximum. The flow rate is somewhere below 50% of the flow. Well, if you have a look at that proportional valve spool, you'll see that it's set to 45% opening. So the valve spool is not even quite half open, and that's because the operator wants to control the speed of the cylinder. So the amount of horsepower, the amount of total energy required to move that cylinder is that diagonal green line that looks at both the flow rate and the pressure. And so our horsepower line, the length of that green line, that diagonal, is representative of how much power it takes to operate the cylinder right now. But what about the entire hydraulic system? The entire hydraulic system starts back at the prime mover and the pump. Well, that is the long, dark blue hypotenuse or diagonal line that you'll see there cutting across the screen. And that's letting us know what's happening at the fluid source, the piston pump. And what you could see is that our pump, a variable displacement piston pump, has managed to match the desired flow rate that it has accomplished, but unfortunately, our pressure is at the maximum value. The pressure compensated pump, you might know it by a couple of other terms as well. Sometimes the term pressure override or pressure cutoff gets used to describe this particular feature. But this is a pump with only one adjustment on its compensator or controller. And if that pump is attempting to go to full stroke, as a single controlled piston pump attempts to do, but the valve isn't open very wide, we immediately hit the maximum pressure trying to push too much flow against that valve spool, and we trigger that maximum pressure compensator. The pump again starts to move towards D-stroke, pressure falls, pump comes back on stroke, and so we stay in a middle of the road displacement. That's nice, variable displacement, but we're always at the maximum pressure. And so we're not saving as much energy as we could. Hey, but at least it's better than working with maybe just a gear pump and a relief valve, right? That's a different game. In that case, all of that blue area above the red would also be red and indicating a fair amount of energy. Because what does a gear pump do? Pumps only at full displacement. And if you decide not to use all of its flow for the cylinder, then it's also at maximum pressure going where?
Right over the relief valve.
Going over that relief valve, and there's your heat. So the pressure compensated pump is already an improvement, but we can do better. So I'm going to click on the button for change to load sense mode. Have a look at what happens to the plumbing near the valve bank. As I click that button, you'll see an extra hose is going to show up. It's a small one. There it comes. A small diameter yellow hose is been inserted between the valve and the pump controller. And that's our load sense signal hose, LS signal. And so that is information that is being fed from the work that the cylinder is doing right back to the pump to help make the adjustment at the compensator on the fly. We spoke about that. Now, it might be most convenient to take the load sense signal right from where the load is being carried. That's at the base of that cylinder. That's not convenient for plumbing.
Not really.
No. So it's typically done with a shuttle valve that is sitting there between the A and the B work port inside your typical load sense valve bank. Not an uncommon way to arrange that. So in simple terms, what's happening here as we look at the energy graph back over on the left, what we see happening is that our pressure now is no longer at maximum. Like the pressure compensated pump, this pump is flow matching our requirements with a proportional valve that's only part way open, but also setting the maximum pressure on the fly in hopes of trimming back the total amount of power that this system needs when the cylinder is lightly loaded. What happens if the cylinder needs to work harder? I'm going to add a brick now. Just going to find my mouse icon here. And I'm going to add one brick. So one brick added to the cylinder, and our business end of the hydraulic system will be working harder. Well, that means a higher load pressure will also be transmitted to the pump through the LS signal line and will give a boost to a spring that is usually set pretty light. Usually that spring is set, what do we find?
Usually a manufacturer will talk about it being between 250 and 350 psi.
What's that? 20 bar for those who want
Yeah,
it as
yeah,
another type
17
of
to
pressure
24
value?
bar.
Yep.
You know, if you're in the metric world.
So that spring is lightly set, but it takes booster value from the load sense signal line coming back from the loaded cylinder via that shuttle valve that's commonly located in a load sense valve bank. So I hope that gives you a little bit of a picture. We could spend more time there. That gets pretty technical, but at least it gives you an idea of the energy savings that are possible, because the idea is not to have the entire system consuming far more energy than what is needed to work with the hydraulic cylinder or motor at any one time. Oh yes, I should probably just point out that the difference between the pressure at the cylinder and the pressure leaving our pump, the fluid source, that's the more commonly referred to as the margin pressure or the differential. Maybe we have our set a little bit wider than 300 on this graph. Hard to say. It's just a relative graph. Gives you a little bit of a picture for how that all works.
If you're working with this animation in Lunchbox, you play around a lot. You can contact us about it. This is one of the more dynamic. There's a lot more going on in this animation than we're talking about today. And just by playing with them, you can't blow anything up. You can't hurt it, I often tell people. But when I'm initially teaching load sense to a group who's just entering into the field, I just tell them to focus around the amount of energy that's being used. That's our key thing right now. So.
Thank you, Mark.
We'll show that.
Absolutely. As Mark mentioned earlier, the symbol on a schematic drawing for a load sense pump is usually quite a bit more complex than that one you saw on the genset hydraulic system. And here on the screen, you're seeing a cutaway of a load sense pump with its two controllers. The one in blue up in that magnifying glass, that would be our pressure compensator, our pressure cutoff, and the one on the right, the load sensing, sometimes referred to as a flow compensator. Well, now we're going to switch over and have a look at a very typical schematic symbol for a load sensing pump. And quite often that symbol looks a little intimidating when you see it on your schematic diagram. But what you're seeing now is just a schematic depiction of a pump that has two pressure controls built in. We're going to assume that you already know a little something about piston pumps and the control piston that's inside the bias piston and how that works for changing the swash plate angle. There you see that pressure compensator. Ours says it's set at 1500 psi. We see we have a load sense setting, which right now is at 150. Hey, I'm just going to move it all the way to 300. And if you're looking at the symbol for the needle valve on the outlet of the pump, and that doesn't come with the pump, but a lot of pump manufacturers will remind you, hey, you're going to have to choose some kind of flow proportioning device to create that pressure differential. That's so important. You have to choose that. And so we've got a simple needle valve in there, but you can see on our live schematic that it says, hey, it's usually a proportional directional control valve that would be sitting there. Okay, and what you'll see if you're looking at those two pressure gauges and the numbers that are there, the pump outlet gauge, the lower one of two gauges, and then the system gauge, we don't know what's happening out the top of this schematic up on the system. Cylinders, hydraulic motors, things that are doing work. But what we do see is that across our needle valve, the differential is being maintained at 300. Yeah, there's little fluctuations happening on the gauges, but that differential is being maintained using the feedback information on that horizontal yellow line that you see there. That's feeding information back into the load sense port. And while you see flow arrows happening on that yellow line, that's not a lot of flow.
No.
If any at all.
It's a sense line that's quite minor in terms of how much flow is actually going there. It's just making up for internal leakage is all you're going to get there.
And it's mostly the pressure value that is being transmitted from the hydraulic system back to the controller on the pump. So the compensator that'll be most active in a load sense system is that one where the load sense port is. It's labeled port X on some pumps. It's labeled LS on some other models of pump.
And
And
not labeled at all on some.
not labeled, yeah. Find your diagram.
Yeah.
Yeah, find your diagram and
You have
find
to know
out
that's what it is.
which port it is. It'll be a smallish port compared to the inlet and the outlet, of course. It's just a control. Let's see, I've got my flow valve set for a particular amount of flow maybe that we want at a hydraulic motor or cylinder. But let's see what happens here as we increase the load resistance out on the system. So somewhere out in the system there's cylinders, there's hydraulic motors. We can't see them in this diagram. It's out of the view off the top of the screen. But as that load resistance increases, the line that says to system in yellow will go darker and will help us adjust the spring side of that flow compensator, sometimes known as the load sense compensator, and makes minor adjustments. And if you're watching that swash plate down at the bottom, its overall angle is changing just a little bit so that those pistons punch that oil out just a little harder, perhaps with a little bit more displacement as the load on the hydraulic cylinders and motors comes up. Hope that makes some sense. Was there anything else we needed to cover on that one, Mark?
Again, just going back to the idea, if you in one of the things that I have found over the years of training people is to keep it as simple as you possibly can, which works really good in my world. Carl, on the other hand, he gets into the complexity, so I just tag along and learn from him. But I'm saying on this one here,
we learn together.
what we've always said about load sense is it's very similar to cruise control on your car. Okay, if you think about simplistically, you just want to set a speed, go along. If you hit a hill, your engine will come on more fuel, more power. But if you're coming down the hill, it'll back off, and then it'll return back to a standard setting. So keep that in mind, no matter how complex the system gets.
We're sensing
It's
the load.
really just sensing a load and telling the pump what to do.
Fair enough.
And
so
we're going to show that.
as we move along here, we're going to bump into some terminology like standby pressure, differential pressure, margin pressure, and hopefully we don't tangle that up for you. We're going to try to keep that as simple as we possibly can. We're going to answer some questions in a few moments that you guys have been sending in. So keep firing those in, and we'll get that all queued up. Maybe just before we get to that first round of questions, let's have a look at one more simulation here. Hey, maybe that's a little simpler. We've gotten away from some of those great complexities of the hydraulic system, and we've gone back to just showing a basic needle valve there, and it's just in cutaway form, not quite so many symbols here. And let's just think about load sensing in terms of this simple system. You'll see that triangle in front of the letter P, the triangle for delta, or speaking to the differential, delta P. We're going to talk about the differential of pressure across that flow controlling needle valve that you see there. And we've got some kind of a magical recycling cylinder that knows how to reset itself at the bottom and head up again. And right now you see that the gauge that's closest to the cylinder reads 300 psi. And as you guys know, as fluid moves past a gauge, that pressure gauge is only reading downstream resistance.
What's ahead of it?
What's ahead of it? Yeah.
Never reads what comes to it. I can't believe how many people we've come across who think that the gauge is reading what pressure is coming to it. It does not.
And that gauge would read 0 if the pump wasn't running today. That's true enough. But after the pump is running, that needle is pointing to a number that reflects the downstream resistance. Quite correct. So that 300, if you're thinking, oh, there's the standby pressure at the pump. No. On that right-hand gauge, that 300 is the pressure it takes to raise the cylinder right now. Let's add a brick. Let's add a brick on top of that cylinder, and our cylinder pressure comes up to 600. So there we go. We're reading the amount of load on the cylinder as we add a brick. Here's another brick, 900. Now, what's really dynamic is if you've been watching the gauge on the left side of that needle valve. What's been happening with the gauge on the left side of the needle valve? It's been matching every change in pressure at the cylinder, but always adding 300 to it. The difference across that needle valve is constantly 300 psi. Hey, would it be a little easier if we hooked up one of those pressure gauges that has 2 connections? Most of the pressure gauges we work with in hydraulics have just 1 connection. But here's one of those pressure gauges that has 2 connections. A differential pressure gauge. And so that type of pressure gauge, and yeah, Mark and I are going to be running one live here in a few moments. Here's a pressure gauge that has 2 connections, measures the difference between one pressure zone and another. Just shows you that difference. And that's the gauge that we've installed below that needle valve. It's showing you that no matter what we do at the cylinder, remove a brick, add a brick, whatever we do with that cylinder to change its load, what you'll notice is that the pump also makes a pretty quick change and as quickly as possible gets back to maintaining that 300 psi differential across that flow proportioning needle valve. That's the basic action of a load sense system right there. Hopefully that makes it somewhat simple. The load sense line reading the pressure loading out the cylinder, moving up and then to the left and into the pump controller and giving a boost to that weaker spring. That was 300 setting. Mark's going to show you how to set that spring in a few minutes here. Add the load pressure to it, 900 plus 300, and the pump moves its swash plate to have the pistons punch at that oil and displace it so that on the outlet of the pump, it's at 1200 psi, 300 higher than the load, and constantly dynamically updating depending on the load at the cylinder. I hope that helps.
Also, look at that as he's adding the bricks and taking them off. Have a look at the action of the compensator, the flow compensator. It's moving down in some situations, moving up in others. And there is a correlation clearly shown here in what happens to your swash plate. Your swash plate will come on stroke every time it drains oil from the control piston on a pressure comp piston, and it'll add oil in and de-stroke the pump every time you want to decrease it. That's the start of all the dynamics that happen within a load sense system. These are crazy fun to play with. If you don't understand them, they're your worst nightmare, okay? Because nothing's going to make sense until you understand it.
Well, hopefully this helps today. All right, Mark, do you have...
Yeah, I got a few things we're going to do here.
Do you have a basic load sense circuit? I think there was a file. I didn't tell the viewers about that at the beginning. So on lunchboxsessionscom/live, where you picked up this video feed, there is a little link in orange below the video window there, and it lets you know that there's a schematic, a PDF file you can download that's got a couple of schematics on it. You might choose to have a look at that one.
It'll have 2 schematics. One that just shows a input with a single needle valve, and then one that shows 2 needle valves. I'm going to be playing mostly with the second one because all it is the first schematic plus another valve. So just to make life simpler, we're trying to make sure you understand what it is I'm actually doing over here on the panel now when we start to play with this system. So one of the first things you're going to notice is on the line that's showing from the HPU, it gives us very specific pump settings. We're saying that we want to set the pressure compensator for the 1200 psi. We want to set the flow rate for 1 gallon a minute, and we want to set our standby pressure on our pump, or margin pressure, or whatever terms you guys are using, at 300 psi. So what I'm going to do is I'm going to start up here. We've got this set up. I've got my pump set up. So one of the first things I tell people, always set your flow first. Flow rates can change pressure readings, so it's always a good situation to just kind of get your flow rate set up. So I'm going to start this system, and what you're going to see is I have this left in an open position, or closed. Okay, so what we're going to do, this pump has a maximum volume stop control, which is controlled by this Allen wrench at this end on this particular oil gear pump. Very common to see. That allows me to adjust the angle of my swash plate. Now I'm going to be able to, I'm not going to play with that today You can see I've got it set, and of course, oil temperature and digital readouts can get kind of finicky. As we teach with analog gauges, people aren't as fussy. You give them a digital gauge, and they'll spend all day trying to make that hit 1 gallon a minute. And as you can see, there are some fluctuations. So we've got our volume set for 1 gallon. Now we got to set our maximum pressure compensator. Our maximum pressure compensator is the system pressure that has to happen at maximum capacity the system is capable of producing. To do that, I must set this pump in a blocked position. I need to block the flow to create the resistance that I want to set. So in doing that, my replication of the schematic, here's my needle valve that's referred to in this drawing as NV2. Okay, so I'm going to reach in here, and I'm going to adjust this down, create a resistance. Let me try, Carl. I'll go on this side. You can watch the pressure going up and up and up. And at this point, I'm going to see a maximum system pressure. And so what I have going on here now is I have preset this before we started today at 1200. So I've got my 1 gallon. I know my pump can do 1 gallon. I know it can do 1200 PSI. So I'm going to back this off, get the pump into a wide open flow condition again. I'm going to shut it off, okay? Now the reason I'm shutting it off is because I have not connected my load sense line yet. This was with my load sense line disconnected. We have a condition that I learned when I was first starting in this business. I was told this is called tricking the pump. I'm going to trick the pump with a signal to match what it's coming out of the pump and try and match that. So I have to change that situation, hook up my load sense line, which is the hose that we're showing today is going to have the orange cable on it as opposed to the red, which is always going to be our maximum pressure line. So I have a situation here. I already know my pump's set for 1 gallon, and I know my compensator is set for 1200. To set this last setting, when we start this up, you notice where the pressure is, and I'm going to come over here, and I'm going to just close off that particular flow control, the N2, NV2, deadhead it, and now I see I've got a pressure up here. On the system pressure now it's maximum, where before it was 1200, now we're down over 300. So I'm going to adjust this on the pump itself. Now this particular pump, which you have to learn which is your controls, what makes things change, best to do ahead of time than to just guess at it. If I were to screw this in, you can see my pressure is going up. Consequently, if I screwed this all the way in, it would go right up to the 1200, but that's not what we want to do. We might as well just put a pressure comp pump on this. So I'm going to back it down till I get near that 300, right, which is going to be close. Now, this is where it's going to be kind of crazy, and we're trying to keep it simple, so we're not going to get too detailed here about where we're picking up the signal from. I'm just saying that's where you make your adjustment. There's my margin set. So my standby pressure, as we like to call it, is now set. No matter what happens, if I block this flow, I can only ever get the margin pressure setting. What happened in the past, we had a service call where a company could not get maximum pressure with a brand new pump. Never said anything about it being load sense. And when I got there, that's the first thing I noticed. We set it all up this way, boom, showed him that he had the maximum pressure he had. He just had it hooked up and he didn't understand it. So what we're doing now is we're saying that in this situation, if I open this valve up now, the gauge itself, notice where my load sense line is picking up here. This is the other end of the orange hose. It's on the T right out of what we're calling on NV2 the adjustable pressure or proportional control. Something, as Carl said, something's got to set that differential. What we're seeing now is a pickup between the 300 and just about 6. Now I can adjust that and change whatever I want in my adjustable pressure control. I will show you that as I turn this up, everything is going down, but that margin, the differential pressure that we had previously set remains there. Okay? And its worst case scenario, when you have no differential, when it's completely closed, you're just going to get your pump setting. So in opening this up,
Mark, and can I just jump in for a sec? So with the valve closed off, cut off the flow there on the needle valves.
Okay.
And so with that cut off, our pump outlet is back to what many would now refer to as the standby pressure. What's the lowest pressure this pump will put out when the LS line is at a 0 pressure, and basically the operator is not attempting to operate any valves, move any cylinders or motors.
This too also shows the energy savings. If I'd have disconnected that line and showed you when I was setting the 1200 at full flow, I would have been into a pressure or a power range. It's up around the 15, 16 amps draw on our electric motor. So this is definitely an energy saving condition right here. You're not doing nothing. You don't need much. It just stands there. Real critical to understand your controller ranges. One of the things that I've seen people try and set that down lower. This particular pump has a minimum range, I believe, of 300 psi. So we're at the very bottom range. You try and get 250, it's never going to happen. You have to get a different control spring in order to make that kind of a range happen. So what we're going to do now is we're going to set that so we get some flow going. We're going to raise the pressure. I'm going to try and raise it maybe to, let's say, 500 pounds. Okay, I'm going to get this up. So now you're seeing my differential between what I set the standby pressure at, which now here we're showing 200 and now we're 500. So there's that 300 gap that we were looking for.
And Mark is just using NV2, a second needle valve, as sort of a highly simplified loaded application, which
Much
could
like
be
the genset was.
it could be the genset. Exactly.
I just got a fixed orifice here now. I just happen to set it where I want some numbers to show up good on the gauges. In this case now, my NV1, which is the load. Carl was using bricks on the animation. Change the load. Well, if I change the load on this simple circuit with NV1, what I'm going to see then is my differential is going to remain the same regardless of what the load is that I'm increasing or decreasing. So if I take that up to 8, 9, can't even read, 900. If I get it up to 900,
Pump outlet.
okay, now we see that we're back at the 600.
The lower gauge.
Again, our 300-pound margin pressure has been maintained no matter what I do with the load. That's as simple as you can possibly get for a load sense system to run your basic examples. When we're in a class training and we've got our equipment with us, this is the point where I just let guys play, turn. They know what they're trying to do. They're reacting to it. We get to see people actually do what they think they understand. And I'll just throw questions like, okay, set the margin for 400 and then prove it to me by changing the load, set up the circuit. We give activities for them, all that kind of stuff. But today we're just going to keep it simple, okay? Simple, downstream T, picking up my signal that's going all the way back. Here's my control port on my pump, and that's connected down into this port where the pump is and the controller. So there's your simple setup.
All right, the basics. All right, thanks, Mark. We got a lot of questions coming in, so we're going to have to get to some of those.
You answer.
And thanks for viewers. I will do my best, Mark. You bet. We'll answer them together, I'm sure. We've got viewers who've joined us since from Panama. Welcome. From Syria, from Pakistan, from the Ukraine. Hey, and Brock, I know you. He's tuning in from Australia, and it's 4 a.m. So thanks for getting up at such wee hours to join us on this broadcast. That's just great to have you with us, Brock. Terrific. All right, questions that have come in. Let's see, where shall we start? Marco, we'll start with a simple question. Who are manufacturers of the pumps that we have here? We have an Oil Gear up here on the table. We have a Rexroth pump over there. Some of the ones I showed you in photographs earlier were Danfoss pumps. We have others here as well in our collection, Nachi, Continental, and lots of manufacturers produce pumps that have a load sense or flow compensating controller. You bet. Andrew says, what happens in a load sense circuit while the system is under negative load? Uh-oh.
There's a good question.
That is a good one. I'm not sure if we prepared for that one, Mark. Hydraulic cylinder or motor running downhill, and it seems to me like a strange thing could happen, like sensing the pressure from the wrong side of the cylinder. Oh, you know what? Yes, we have. We've bumped into that.
Yep.
Not on an open loop hydraulic circuit. We've bumped into unfortunate circumstances like that that you're describing on closed loop hydrostatics, where a runaway on a hydrostatic controlled system, closed loop, with a pump that had dynamic controls built in, did end up sensing from the wrong side, and instead of de-stroking the pump, moved it to maximum stroke, and basically picture a train wreck at the bottom of the valley. Very dynamic. But to get to the fine points of what you're asking there, Andrew, basically whenever there's going to be a downhill or a runaway, a negative load, as you mentioned, quite often there is some other valve elements brought to bear that help control that runaway effect, that bring some motion control in, and you might know that type of valving as a counterbalance. Sometimes that's built right into a hydraulic motor package. A hydraulic motor package for something that has a track undercarriage or a wheel drive system will quite often have a motion control or counterbalance valve system built right in on the motor. Sometimes it is plumbed externally. But yeah, things do get very dynamic, and the load sense system isn't necessarily set to do something useful for you under every condition. So that's where the additional element of the counterbalance or some other controlling valves come into play.
But the counterbalance would also create that resistance. Depending on where your sensing line is picking up at,
very good point.
It's going to tell the pump what you want it to do, because the counterbalance valve will close off as the machine is trying to run away downhill, creating that almost a braking action. Sometimes it is referred to as a brake valve, but no matter what you call it an Aunt Sally's chocolate cookie valve, it doesn't matter, it closes and starts to create that resistance so oil can't just run away and drop your system pressure. This is the complexity you have to get into an individual circuit, and we'd certainly be willing to help you understand it.
We have a question from Ale Abu Kurj. He asks, I think he's referring to this particular simulation now that I see the question. What's the function of the 3 orifices in the right of the schematic? Yeah, there's a bunch of things going on here. Well, one of these orifices, the one that I'm circling with my mouse icon at the moment, my mouse pointer at the moment, that particular orifice is there to bleed down the load sense signal when the directional valves on the system is put in neutral. When you put your directional valves in neutral, you want your pump to idle down to that low standby pressure Mark was showing you. And so you want to get rid of any remaining load sense pressure in the line. And sometimes that bleed down orifice is inside the load sense valve bank. And sometimes it's in the pump. And you just, the designers, the system engineers will make sure it's somewhere. It's not always in the pump. So sometimes this orifice is crossed out with a big X to let us know that that one has been blocked off, and then you would probably notice that your load sense bleed down is elsewhere. In fact, I'll show you that in a moment on another example for another system. So that's that one. Let's see here. Mubarak Hussein asks why there are 2 orifices at the pressure compensator. What happens when you remove them? Okay, so more questions about these particular control orifices. Sure. Well, control orifices come into play for a number of reasons. They can be there to help dampen the action of a control piston so that it isn't overly reactive to every little pressure change that occurs in the system, and to slow down the action so that the pump isn't overly reactive. Okay, why does it twitch? The swash plate, I think, is a question coming in from Miksa Kranovoy. Thank you. Why does it twitch? The swash plate angle, perhaps? Yeah, that's a good question. Well,
I asked that same question when I first joined, Carl.
Yeah. Well, when you're watching these symbols in the pump schematic and you see that the symbols for the compensators are moving back and forth, it makes it look like there's some giant 3-port, 2-position control spools in those pump controls or compensators, and you're almost starting to picture some big directional valve spools up in there. If we had more time, we would zoom in on all kinds of little details. But if you've taken them apart, you'll know that these compensator spools are the diameter of a pencil, smaller even, and very small land surfaces on those spools. And in most cases, they are zero lapped or critically lapped with the control ports. And so the movement of those little spools is actually very tiny. And those spools remain very active, continuously making minor corrections to what is happening with that main control piston. And if that main control piston is receiving corrective signals, then the swash plate is also moving. But in the case of many of our simulations, we have greatly over-exaggerated the movement of the swash plate so that you can understand better which way that swash plate is moving. And in fact, in many cases, the swash plate may be in a middle ground between 0 and maximum angle on many pumps is around 20 degrees. It could be in the middle at around 10 degrees, and that if you and I were to get inside the pump at any one moment, it may look like the swash plate is standing still or just barely moving at all.
Keep in mind, too, that on the symbol itself, it shows the double parallel lines, which indicate that that spool is infinitely positionable between all the way open, all the way closed. Our animations generally will just show you that it's moving between giving it some oil or taking some away. So we just expand it all the way so that the lines line up.
Very good.
Often you'll see a pause feature on some of our animations where you can stop that from happening.
Stop action,
and look. So.
Yeah, thanks. Hey, our good friend Sammy from Tunisia asks, with cranes, there are many cylinders and motors that can be in action at the same time. Yeah, that's called multifunctioning. Yeah, you know where we're going next with this, Sammy.
Slow down.
Yeah, no, he's got it. He's right on top of where we're headed next, isn't he?
We are getting there.
Yep. And the pump compensator is connected to the manifold, and there's a load sense orifice, and he's saying, and there's some shuttle valves. So can you give us an example with cranes? I'll give you an example, you bet, with multi-function or multi-section valve banks. A 2-section is all we're going to have time to get into, and we're going to have a look at those features here in just a moment. So yeah, you bet. Stand by for that one, and let's just keep that question on the screen, and we will do that. Why 15 to 20 bar LS compensator pressure? Why not lower or higher? Yeah, that's really good. Okay, so for that question, and that's a beautiful question, let's go to this one. So if you're seeing the delta P and load changes simulation on the screen, then you're seeing one that I like. I'm going to remove a few bricks here, and now I'm going to do something in this simulation that I didn't plan to do, but I'm glad that you reminded us to do that one, and we're going to drop a brick from the sky. So here comes a shock. Watch those gauges, especially watch the gauge to the right of the flow controlling needle valve. Maybe watch the gauge on the left as well, but just watch and see whether or not that 300 delta P can be maintained as we drop a brick from the sky. Oh, what happened there? I hope it played in real time for you, as it did for me, real time in our simulation, that is. When we dropped this brick, this next brick, that 600 turned into a massive spike of 1200, which for a moment was higher than the pressure controlled leaving the pump's outlet port. Uh-oh, what happens? Well, for a brief moment in time, until the pump responds and upstrokes and changes the position of the swash plate to punch that oil out at a little higher pressure, for a brief moment in time, flow through that needle valve stalled. That translates into a cylinder that stopped moving. Now, for the operator of the excavator or the crane or whatever type of machine, did they actually see that the cylinder stopped? No, it was a very short duration, but maybe now the operator calls in and says, wow, I'm getting some really uneven motion, some very bad shocks to my machine at times. Well, this could be an indication that maybe somebody set the margin pressure too low. If you're going to have some fairly extreme changes in pressures out on the hydraulic cylinders or motors, you might need a wider margin. On the other hand, if you know that what your cylinders and motors do are never going to encounter any unusual shocks, you might be able to trim that margin right down to 10 bars, 12 bars. We've seen some load sense systems.
It's an energy savings.
Oh yeah, right, yes.
Especially on mobile equipment, that's fuel.
If you could get it down to a 10 bar or 150 psi differential and you never have any shaking or jerking on your cylinders, especially while multifunctioning, then great. You're going to save a lot more energy. On the other hand, Mark and I have run into some machinery in the oil field where there was only one or two off, a very unique design machine, had a tough time getting all of the fine points of design and engineering done, ended up having to set the margin at 700 psi. Almost no savings to be had now over just having the pressure compensated pump, and forget about the load sense. So yeah, great question. I hope that answered that a little bit.
I'll often talk about that difference of where you set it as kind of a way of setting the sensitivity of the system. You know, you're having these changes. If you have a little change, nobody really cares. But big changes can make things hunt. They can make it do a number of things. So setting the sensitivity by using and understanding these different margin and standby pressures is very helpful. And often we have seen in manufacturers' catalogs, they'll say that this pump has been designed hopefully to address all of your conditions, but you may have to make some adjustments to it. And this is where everybody's kind of getting left out hanging if you don't understand what's going on in the first place.
Lots of other questions. We might have to move on for a little bit. A question that came in from Kike, and he is asking, I believe, if a 4-port 3-position proportional valve is open P to A, okay, P to A flow, so that's going out to our cylinder, and there is a 300 psi pressure drop across the spool, I'm assuming. Does that mean that there's also a 300 psi pressure drop on the oil returning across the spool T to B? No, not necessarily. No. Mark, how do we answer that one?
I'm just trying to visualize that in my head.
Yeah, the load sensing aspect of controlling an actuator while it's moving is done across the spool on the side where oil is being delivered to the actuator. I hope that's going to be adequate for now without overcomplicating.
You could be getting into areas that are often talked about: pre-compensation, post-compensation. Where are we picking things up? All kinds of terminology.
Good one.
For nothing else we say today, there's some new words come into your language when you start playing with a load sense system. And I spend a lot of time trying to understand what this manufacturer is talking about. But once I break it down into a simple function, I just realize Parker calls it different than Rexroth calls it different than Eaton or Oil Gear. Everybody has their name for what they're trying to describe, but if you back up, you're just going, no, they're just talking about the difference between here and here. And so terminology can really throw you off until you get used to it.
Hey, Mark, can you help me out with this question? He asked, did Mark have the load sense adjustment at the maximum when he adjusted the pressure cutoff? No. You had the load sense line unplugged, right? Yeah.
Well, wait a minute. Load sense adjustment at maximum.
When you adjusted the pressure cutoff.
I have it disconnected totally. I vent it is actually my preference for setting compensator settings, which is the maximum system pressure. When I use the term tricking the pump, I have to get a signal or create a condition where the pump, instead of trying to get to 300 and then de-stroke, you're actually trying to get it to chase itself. And this is the tricking, what I call tricking. What's happening is the pump is trying to reach that next pressure and just keeps going up. So how do I do that? Well, I take part of my P signal, my output of my pump. We have our power unit set up where we can just flip a valve and trick the pump. When I used to work in one plant, we used to have a separate hose that just stayed plugged. We would tee it in before the load sense and just send us a solid signal, and it will go to maximum at that point. I hope that makes any sense at all.
Great, thanks. Hamza, Mark, trying to keep track of this question too when we're running the vertical lift with our two lifts. Hamza is interested in knowing if the pressure differential will be showing when the cylinder reaches the end of stroke.
We're going to show you some stuff on that.
So when we get this vertical lift going here very shortly and we run to the end of stroke, we'll try and remember to keep track of that question, and we'll look at a pressure gauge that is reading from the very bottom of the cylinder, not just the delta P. So that's a good question.
In fact, I used that situation as we were preparing for this video to create a new activity in training where I take people on a level 3 where we're expecting them to understand a lot deeper. I'm going to have them try and explain to me why this is happening. And that's a whole other thing that we'll get into here in a minute. But Carl's going to do a
Yeah. Okay.
a
So
multi thing. Yeah.
hopefully we answered some of your questions
I
there.
love it. People are asking questions.
And new viewers have joined us from Superior, Wisconsin. Hey, from the state of.
Lived in Kenosha for a while.
Did you?
Oh, yeah.
There you go. The state of cheese and beer and wonderful things.
Bratwurst.
Yeah, bratwurst. All right. Let's go on and have a look at a multi-section simulation for a load sense system. So hopefully what you see now on screen is a pump on the left-hand side with some yellow lines. And over on the right, you see a couple of hydraulic motors. And as you know, we like to put brick stackers. We put a brick stacker on top of our cylinders so you have some way to easily imagine where increased pressure came from. Well, we've done the same with these hydraulic motors, except that the hydraulic motors have a brake shoe. I don't know, I guess we'll call it a brake shoe brick stacker. And so picture that brake shoe there on that left motor and a brick stacker platform, and I don't know how there's a brake shoe rubbing against a hydraulic motor symbol, but it's
We
what
live in and not the real world sometimes.
well, yeah, not the real world, the simulated world, exactly. So we've got that proportional valve on the left side rolling. We've got that left motor running counterclockwise, only one brick on the stack. And then I'm going to, maybe we'll just increase that left valve resistance a little bit. We'll put a second brick on that one. And then on the right-hand valve, so now we're multifunctioning. And Sammy's question, I think, had to do with multifunctioning. So hopefully I remember how to answer that question. And
This is
so
the crane? The crane?
the
question?
crane? Yeah, okay, yeah. These will be crane winches, Sammy. These will have to be crane winches. All right, so on the right-hand side there, we've got a motor running and only one brick on the brake shoe brick stacker, so lighter pressure. And you can see also some differences there with color, so hopefully that helps. You will also see some valves that look like a shuttle valve. Nope, they don't look like a shuttle valve. They are a shuttle valve. And a little ball that can move back and forth, can shuttle back and forth in there.
They were called. I've been calling them that for years.
Yeah, shuttle valves. Well, what else have we heard them called? Ball resolvers?
Yeah,
There's
resolvers
a few,
if you're Caterpillar orientated.
There you go. There's a few other names, maybe. And what I want you to do, though, is watch those two shuttle valves. Maybe watch primarily the one on the left. Watch the shuttle valve for the motor on the left, or the valve application on the left. Watch that one as I overload the motor on the right. I'm going to really stack up. Oops, let's see. I've got to get on the resistance here. There we go. Second brick. I'm going to add a third brick. I'll back off. There we go. The second brick and third brick. And watch that shuttle valve on the left-hand side. It moves down when the motor on the right is now the section of the valve bank that's at the higher pressure. What these shuttle valves do, this is a resolver network, as it's often spoken of, and what these shuttle valves do is it allows the valve section in the valve bank that is running the actuator who has the highest current system pressure to be able to report that highest system pressure to the load sense port on the controller way back over on the pump. So if you'll follow with me for a moment, if you can see my mouse pointer, we'll move back through the shuttle valve on the first section, then through a filter screen. Hey, there's that bleed down orifice, you guys. Instead of bleeding down inside the pump, this one bleeds down the LS line, the LS network line when the valves are neutral, bleeds it down inside the valve bank, and then down and out on the LS line, and there's our signal hose, and report that to the pump. Now, if the hydraulic motor and the valving on the right are in charge of making the pump change its position a little bit, watch the swash plate on the pump on the left as I play with the resistance here on the right-hand valve application. So all of the instructions for what the pump should do are coming from the valve and motor application on the right in the valve bank. Well, if the pump upstrokes a little bit, does that maybe mean that the motor on the left might speed up a little bit because the load on the left motor didn't change? Well, that would be undesirable. Just because the pump was compensating for extra loading on the right-hand valve and motor application doesn't mean that the left-hand motor should speed up. Let's see if there's something that helps us with that. What's jittering down here at the bottom? What is that? That little box that's jittering down there at the bottom near the inlet to the left-hand valve and motor application, that box is receiving, that symbol is receiving some of its information. I'm just going to run these valves at full speed so that our proportional ports all line up. I know that helps. That valve is receiving some of its load information through little holes that are drilled in the spool. Mark might show you something there. And that dynamically sets a valve that maybe looks a little bit to you and I like a pressure reducing valve, except that its control signal is coming from the load side of the valve. You guys know what that is. Yeah, that's right. I've been teasing you. You guys know exactly what that valve is. Thanks, Mark, for reminding me to zoom in.
I'm old. I can't see it that far away. So
right. Let's zoom in. That jittering valve is the compensator, right? That is the pressure compensator that precedes the inlet to the valve spool. So this is a pre-compensate example. And it is making sure that even though the right-hand valve and motor application are talking to the pump right now, higher pressure, that things don't get disturbed for flow rate across the valve spool on the left proportional valve and motor application in this multi-levered valve bank that we're working with. So that is pre-spool pressure compensation designed to keep things nice and accurate for flow passing through this left valve application. I hope I'm answering some of the questions that were being asked about that. And I know somebody is going to pop up and ask, is there sometimes something called post-compensation? And post-spool compensation means that that compensator would get moved from being before the P port on the spool to being on the A or B, both and typically, work ports, leaving the valve going to the motor. That would be a post-compensation, a post-spool compensation scenario. Very popular on Komatsu machinery, shows up on some Caterpillar machinery, and quite often that post-spool compensation is there to really help make sure that flow is adequately proportioned to all the valve sections and actuators if all of a sudden many sections are open, many applications are running simultaneously, and perhaps some of those applications are at a very low pressure, which might cause stalling for the higher pressure ones. In some of those cases, post-compensate can be the one that is the better one in that case. Generally, for really accurate compensation, quite often pre-spool compensation is better at dealing with a great variety of pressure and loading variations. So different valve manufacturers often offer different approaches to that aspect of it. Where are we in our list of topics, Mark? We better keep moving, eh?
Yeah. Keep in mind that is just what he talked about in the beginning about a pressure compensated flow control, how simple that functions. There's pressure on one side and then a lower pressure and a spring on the other side trying to position that spool to just the right place to give us the differential we're trying to create. And so this is very dynamic. Anything hangs that all up. Dirt is your worst nightmare in these systems because if that spool hangs up and the differential changes, the pump's going to see that and try and make an adjustment for that, and everything's going to go crazy on you.
So just to help make things simple once again, I have put up on screen here, not a load sense system, just a component. Hopefully you guys can see it. Mark will point it out. There we go.
Right here. There, the little machine.
Yeah, there it is. This is from the Parker Color Flow series, and that is a pressure compensated flow control. Looks just like a plain old ordinary needle valve from the outside, but this particular model with the rounding that you end up with on the inlet port side lets us know that it's pressure compensated. So what you're looking at right now on the screen, you're looking at a scenario where we're just controlling flow. This is just the pressure compensator, and you're thinking, did something happen? Did our proportional valve spool disappear? I guess you could say it did, but there is still a flow proportioning device. It's just it's a needle valve now. So look what happens as we add bricks to the hydraulic motor brick stacker to induce a higher load pressure, there is a load sensing passage here, adds to the spring, and makes an adjustment on the inlet side to set up a higher pressure before the needle. And what you will notice is that the pressure drop across the flow metering needle valve stays pretty close to 100 psi, whether we remove a brick or whether we add a brick. And that's because there's that extra compensator spool inside this flow control. So once you get inside a major pressure compensated capable load sensing valve bank, that's all that's happening. Let's not overcomplicate that. And I think that's where we sort of pass off some of all these features to Mark, because Mark and Nathan here were busy working on a new cutaway, and I'll let Mark take it away and show you some things about this one. Inside, to make some sense out of symbols and a cutaway.
Yeah, one of the more complicated things that we can see happening when you actually start to use a schematic to help you understand what's going on, you have to learn how to read it properly. You have to understand a lot of things. From our experience working with people, mostly from myself as a person who is a visual learner, not a book learner, I need to see some things. And so in these animations, what we're talking about here, this is the one section of this particular valve right here. I had it apart this week. This is the one that's got the feed reducers on there. And so what I'm going to do is just run through this very quickly with you to show you some spots. And one of the things that I have really enjoyed working here and developing stuff like this is to bring that gap that's missing between the mechanic or millwright into the hydraulic system. So when we look at this part, I'm going to start out by just looking at the spool options. Well, if I move my spool nice and slow, as Carl teaches me sometimes, if I mouse over that spool, you can see down in the schematic representation, that's the part we're talking about here. Okay, that's the representation in the schematic for that. If I mouse over that part and say, well, what is this piece doing? It tells me what part is visually in the break and cutaway image that we have with it. So there's your main spool. Currently, right now, we have a motor spool depicted in here. So that's a spool that has all four ports open so that things can coast to a stop, that type of thing. Or it can have many other variable configurations for spools, as most of you are well aware of. Then, as Carl just pointed out, I'm going to zoom in here for a minute and drop this down. Okay, so now when I put my mouse over this part, you should have been able to see the comparison between the control spool, compensator spool, and the spring, which is being fed from a pressure and forces inside and opposed from a signal that is coming from the shuttle valve onto this side to give us that compensation function that says, give me just the right amount of flow to create the pressure drop I'm looking for. In this particular spool, what's really unique and drove me nuts in the beginning was zooming in and realizing these little tiny holes that are drilled into the spools. There's passages in there. I had to try and figure out where they were. And those holes are small enough that this little wire is the only thing that fit in there to help me decide and blow air in there to figure out where does it come out once I blow it in here. So it's a fun thing to do and investigate these things. There's our little shuttle valve that we're talking about that'll move. I'll show you that in a second. But also look at the schematic representation. If I bring this down, when I put my valve, you didn't lose my ball, did you?
Nope, hope not.
Okay, good, stuck.
A little tiny.
Yeah. So when we look at the spool, this is the symbol. Again, it's picking up a signal from the spool body itself on one side, the main pressure coming in on the other. It looks like a pressure control, normally closed pressure control, but it does give you that variability. In this particular valve, this also has a load check feature to it. Okay, when this valve saturates all the way to the back, and I'll make that move in a minute, then you can have a situation exist then where your load is held properly, and if you needed to start an engine when it's under a load, this will allow you to not sense and have your load drop, so a load check function. I won't get into too much on that today. Then we see these other little valves. I'll back out a little bit more so we can see where these are. These are your solenoid, proportional solenoid controls. that send pilot pressure to both sides of the spool to allow it to function. And we already talked about the resolver or the ball valve here. I want to show you this one. This is a common problem for load sense. If you have, for some reason, took your control valve apart and you are not aware of this little ball that's shown here in the check, if you tip that, Carl, you'll get that to come right out of there. Okay, that's a little tiny ball. It's 3/16 of an inch in diameter. I had a customer one time, they said, we took the valve apart, we can't get nothing to work now. Well, not only did they mix their spools up, they'd lost half of the balls in an 8-bank control valve. And when I asked him about where are all the balls, the guy goes, what balls? So when those fall out, if you're a mechanic, go to your local bearing house, get yourself a bag of 3/16 balls rather than look for them.
If that's the diameter. Mark, haven't you and I come across some that have smaller diameter in some, eh?
Well, in some of the newer ones.
Yeah.
Now they make these now in a little kind of a cartridge that's pressed in. I know this Parker valve has that. Like you're not supposed to take it out, and the only way to get it out is to damage the valve.
So hopefully it wouldn't even fall out.
Yeah, you wouldn't fall out in some of them. But
no, that's good.
This is one that I've really had a lot of issues with over the years. So when we move this valve, we have our control feature here where we can shift this back and forth. The arrows show you the flow in all the applications. We can create the resistance, and we can put a load on the cylinder as well as change the pressure that the load sense signal is seeing. So you're going to see movement of various things when you play with this. I won't spend too much time on this today. This is going to end up being a whole nother lesson in itself. But when we look over here, this is a very interesting feature. These are your feed reducers, they call them. And what they do, in essence, as far as I can tell right now, they end up being a pressure-reducing valve. This valve has two of them. So one is for the A port, one is for the B port. This is not a port relief valve. This is a way of limiting the pressure in A or B or both to a preset limit so that you can keep main high pressure in the rest of the circuit, running everything else. So it looks very simple. If you zoom in on that, if you look, I'm used to using my other machine. If you look at these, they kind of look like a relief valve. You can study it farther, but it picks up a signal in the port. These are your work ports, or your port reliefs, I should say. Right? When we move these are, again, a cartridge made by the manufacturer, set at a given pressure. You have to make sure you don't mix those up because these are set at 2 different pressures on this valve, as well as my feed reducers are set at 2 different pressures. If you put them back together wrong, you're going to have all kinds of problems as well. So this valve is, again, the later technology. It's pre-compensated, as we talk about that. It's for each spool, has its own compensator. The inlet and outlet features of this valve have multiple options for them. It's amazing the complexity. All the manufacturers of this series type of valve, you're seeing just immense amount of options available. And you cannot mix them up. You do need to know what you're playing with.
Okay, great.
That's all I'm going to say about it.
Okay, thanks, Mark. That's terrific. So you've had a look inside a typical
one last thing.
load sense valve
In
bank.
the inlet, Carl was talking about how you can have multiple functions up to the volume of the pump, maximum volume of the pump. But if you have a 5th, 6th function that you pull and need more, and it's a lower pressure, you can get into what's referred to as anti-saturation. You need special controllers for that, which have to do with pressure compensators. And we're just going to leave it at that today.
All right, so we're getting close to the maybe the moment you've all been waiting for, where we're going to run a vertical cylinder application, a single rod cylinder. We're going to run it unloaded for a moment. It's going to lift. It's all of a sudden going to come into contact with the first 100-pound steel block. It's going to pick that one up, and then a short while later it will pick up the second block. It will add a load. So we've got a live brick stacker planned for you here, and hopefully that's going to help answer some of the remaining questions that we've got. Unfortunately, we probably won't have time for too many more questions today. We've been running on long.
But you can always email them.
Yeah, if you don't get the answer to your questions today, then feel free to email us, and we will try to catch up with you, and perhaps we'll answer a few more questions here as we run our last application. Now, some of you asked questions about jittering of pressures and what have you. as the system runs. I just want to explain a little bit here. Oh, and maybe I should have played the 3D movie of our load sensing lab setup. So just to give you guys, the viewers, a little bit of a clear sense of what's going to happen, I'm going to run this video, and you can see there's the cylinder headed up, and it's going to make contact with our first brick. There you saw a little shock because it's steel on steel. The second one shows a little shock, but I think when we run our system, you might see that because of our rubber cushion there, that second little shock on our delta P gauge might not even happen just because we managed to cushion it. I'm going to run that again for your benefit. Let's run that one more time. Watch the delta P gauge. The load sense line, in our case, is coming right off the base of the cylinder in the orange banded hose. That's the load sense. So we're sensing the load right at the cylinder. And why are we doing that? Just to be as addressable with our application. Also, the proportional valve that we're going to open only partially to get a nice slow speed is just a very basic proportional valve spool. It doesn't have all kinds of shuttle valves in it, doesn't have pressure compensators, but that's okay because our application runs in a pretty controlled environment. This isn't a very dynamic environment. We're not digging in the earth where things continue to change. Things are very constantly set. Also on the bottom right-hand port of our cylinder here, our gauge on the left of this panel, this digital gauge, is just going to show us the pressure of the base of the cylinder as we pick up one brick after another. So maybe I'll get Mark to start it up now.
I just want to say something
Go
before
ahead.
we do start. In this particular video, if you show over there, we have removed, this whole operation is generally, as the 3D video shows, is in the back of this panel. We brought this out here just to be able to show you. We've taken the cover off because we had to do some things in time. Normally this is completely enclosed. You can't put your fingers in or do anything to pinch or
We'll be careful to keep our hands out.
Yes.
You bet.
We're
Okay,
gonna be moving slow.
so Mark, as you put oil into the base of this cylinder using the proportional valve P to A.
And this is a 4-port 3-position valve with all ports closed.
Oh, yeah, there we
center.
go. There's your symbol. We're going to
sure.
run that P to A. We're going to put flow into the base of the cylinder. And for the first go around here, I'm just going to have you look at the overall pressure from the base of the cylinder in the left digital gauge here. And that pressure is going to continue to increase as we lift one brick after the other. Go ahead, Mark.
Okay, keep in mind too, I haven't changed this pump. We already preset this earlier, so you know what this pump is set for.
Well, we'll get to the delta P right after that. Yeah, you bet. Okay.
So
let me just turn the lighting on the gauge here. It helps a little bit, causes some flickering too, but maybe we'll see it. Okay, go ahead.
Do it nice and slow.
Nice and
Stand
slow.
back.
So just 40 psi. Contact the first brick, and we're now at 200 psi. And second brick, and now we are at about 350 or 400 psi.
Now, a question was asked earlier about what about the pressure at the end of the stroke? I just wanted to point out right now, I don't want to answer the question yet, but notice over here, we're at a maximum pressure. Our compensator setting at 1200, which is not typically where a load sense system would be set for, but it is have that capability. Now, when we run this back, we're going to bring it back the other way now. Nice and slow. Stand back. And we see that we're going to leave the bricks in the air now.
One brick left behind.
Pressures are dropping because of the requirement necessary. Now watch what happens when it gets to the end of this stroke. You can hear it. You can see it. It's pretty low. It's back into the setting that we originally were setting our pump in a block position.
And that is because currently we have no load on the base of the cylinder.
My control pump pressure, the signal that's coming back to the pump, is reading 0. Okay, now keep in mind we're using digital gauges over here, differential gauges and analog gauges, and so don't get too carried away on how exact the number is right now. But look at the differential gauge, but look where the differential is being taken from. And also, the sensing line right now is on the return side of this valve now. When the spool is shifted, now we're P to B, A has got no pressure in it. So therefore, the pump will de-stroke to its load sense saying, you don't want much, I don't give you much.
Time to stand by.
Time to stand by and wait for something to happen.
Okay, so yeah, as Mark pointed out, the two microbore hoses are connected from P across P and A ports on this directional valve, proportional directional valve, and those two microbore hoses are connected now to our delta P. And so this time, instead of watching the maximum loading of the cylinder as we lift the steel bricks, all we're going to watch is what is the differential across that proportional spool. Is it maintained as the cylinder goes from being unloaded to loaded with one brick to loaded with a second brick? Okay, Mark, go ahead, and we'll just watch the delta P gauge. He's going to run it as slow as he can.
It's a very touchy control right now.
So there you go. The first shock, and that was steel against steel. And the second one, you may not even see a little shock. And the delta P was maintained as we went and picked up both bricks. So even though the load kept changing,
notice that
the delta P did not. Yes, the load sense line now, or the delta P across the proportional valve is now 0 because there's no flow passing across the proportional spool we've deadheaded.
There is no differential.
Do you want to run it one more time?
Absolutely.
Take it all the way down, and we'll run it back up and see load sensing in action. And of course, we're seeing things all from the cylinder's point of view, or out here near the cylinder and at the directional valve. But as you guys know, that load sense line is connected back to the source over on the pump control line. And it's a dynamic system, closed loop signaling, if you will, even though this is open loop hydraulics.
So we show the pressure, but it's not necessarily a differential pressure at this point. It's the pressure that's in this line because we are
here we go.
side.
So the cylinder starts to come up as slow as we can. There we go. Here it comes. And the first time we make contact, we might see a little bit of shock. Just a little bump. There it was. Steel on steel. As we pick up the second brick, we've got a rubber cushion in there. So you may see no bump on that delta P gauge. Nice, smooth load sensing action was maintained the whole way up.
Speed doesn't change. Pump is being sent a signal that says, you only want to move this fast, that's all I'm going to do, regardless of our load changes.
The flow rate nice and steady. All right, we're winding down. We've shown you what we wanted to show you today. And of course, there's many more learning materials for learning about load sense hydraulic systems in lunchbox sessions, many more things that can be learned about hydraulics overall. So feel free to explore those possibilities. And if we didn't showing you there, we thank our sponsor today, Oil Gear, our friends at Fluid Power World, fluidpowerworld.com, and also thanks to the team here at CD Industrial Group that produces Lunchbox Sessions. We are Carl and Mark and Owen, as well as Nathan, Crystal, Robin, Chris, Ivan, Alex, and Lenore. And special mention also to Ted, Keelan, Emily, and Grant for their contributions throughout the past year. Hopefully that's been helpful for helping you with your learning on load sense hydraulic systems. Feel free to communicate with us further and watch at lunchboxsessions.com/live. We hope to have, we should have out shortly additional topics and dates throughout the fall for additional live sessions. Thanks so much for joining. Mark, thanks for assisting me today. That was great. We hope to see you all again soon. Bye-bye.
Bye-bye.